Yes, sir.
Okay. Okay, so let us begin with where we left yesterday. So I will just quickly revise what are the steps involved. So we were discussing this importance actually for generating equilibrium configurations for equilibrium configurations. In this particular case, I mean, this method is more general, but we are doing for Ising model. And the main idea is that the samples themselves, one second. Oh, Bhaiya. Okay, yeah. So we were generating samples which are occurring with the frequency of their Boltzmann. When I say Boltzmann wave, that means they are occurring with this frequency of e to the power of minus beta t, and whatever is the energy power, for that state. So if when you are choosing the sample themselves are coming with this correct Boltzmann wave of e to the power of minus beta t, and so in this particular case, if we want to find out average of any of the samples, so for instance, if I want to find out average energy, all I have to do is take, let's say, total nk number of, let's say, ns number of samples, and then whatever is the energy that you get for, sorry, this is E of t. Then whatever is the energy for each of the sample, all you have to do is you just add all the energies divided by the total number of samples, and that would give you the correct average energy for the system. Or for instance, if you would have wanted to find out the total magnetization of the system, then what you would have done is you would have added all the spins, and so this is, I mean, recall, if you have to find out the total magnetization, then you have to find out the individual magnetization for each of the samples. I mean, here I'm talking about the total magnetization. And then again, this K sum goes from N to S. Of course, you notice the change that because you are already, the samples themselves are occurring with this particular frequency. So unlike where in the partition function or calculation of average energy, I mean, if you recall, for instance, if I had, this was, you had to actually multiply this factor of e to the power beta I, and then this thing in order to calculate the sample. But because the samples themselves are coming with this weight, in this approach, you don't have to again multiply it with e to the power of minus beta. So this was the, as far as the conceptual issue of how these samples are done. And then just to revise quickly that how you operationally actually do it is that way of generating steps for generating the samples for, in this particular case, for the case of importance sampling. So step one is initialization. And for initialization, all you do is, I mean, assign the spins, or rather place the spins with random orientation. By random orientation, that means you either place them up or down. That means +1 or -1 at each lattice side. This was step 1. And then from the step 2, you first calculate the energy for this configuration. And this is, of course, we had discussed that, so if you want to calculate this energy, then one of the summation runs from I to n square. That means the total number of lattice points and total number of spins. And then this J index goes from 1 to total number of nearest neighbors, which for 2D Ising model just happens to be 4. And then you have this SI, and then you basically sum over all the nearest neighbors, and that gives you the form of calculating whatever is the initial energy of the system. So this is step 1, step 2, and then from step 3, it's basically where you actually, step 3 starts the dynamics of the spins. That means when I say dynamics of the spins, remember that each of these spins can actually flip from upstate to downstate, and how it would happen would be determined by this Boltzmann rate. And in principle, in particular, how you will do the dynamics, and that is what constitutes this important sampling is, first step is you choose a particular spin at random. And when I say random, I mean of the n square spin, any of the lattice sides among this n square side, you choose with equal probability any one of these sides. So particular spin you choose. And once you have chosen the spin, you do trial move. What do I mean by trial move? You flip the spin. Right? So if the chosen spin happens, then you make it down. If the chosen spin at that particular site was down, you just flip it and make it up. So that is the trial move. So this is the fourth step. Let me just write the fifth step here. So now you have to check. After you have flipped the spin, you calculate the energy for the configuration with flipped spin. Let's say I denote it by EF. This EF is of course a function of whatever is the configuration after you have flipped that one spin. So you calculate the energy with this. Then if I want to sort of break it up, you calculate this energy difference. That means after you have flipped the spin, if this is the final energy after flipping the spin, and you subtract the initial energy of the system before this flipping has happened, and so you calculate this quantity delta E, which is the energy difference between these two configurations. And then what you do is, if your final energy EF is less than the initial energy, that means if the final, you find that after flipping the spin, if the energy that you calculate for the system, if that is lower than the previous configuration, then you accept the move. Then accept the move. What I mean by accepting the move is that, remember that at this step 4, you made a trial move and flipped the spin. So now when I say accept the move, that means whatever after flipping the spin, whatever configuration you got, that is like the new configuration of the sample of spin that you have. So that is accepting the move. Else, that means if EI is less than EF, that means if the final energy after flipping the spin, you find that that configuration has an energy which is greater, then you call call random number, uniform random number, let's call it R. And if you find if R is less than e to the power of minus delta E, that means exponential of minus of EF minus EI, then you accept the move. Then accept the trial move. Else, reject the move. When I say reject the move, that means when you flip the spin, you do not accept that configuration. You go back to whatever configuration you had initially had just at the previous step. So if this condition is not satisfied. So if this is not satisfied, that means you find the random number greater than this. That means basically that means this event has not happened. You reject the move. And after you have done this, you again, you again sort of go back to step 3. So after step 7, 8 is basically going back to step 3. So once you have gone through this trial move, you again, what you do is you again pick up spin at random, and then again you would again flip the spin, do this exercise, and keep on doing this. So this was as far as all the steps from, if you think from 3 to 7 and then this repeating process, this is really constitutes what how you are performing the dynamics of the spin. That means how these spins are flipping at a given temperature. And remember, in principle, if you wait for, the notion of equilibrium is that if you wait for long enough time, then you would reach the equilibrium configuration. So in the similar spirit, if I had continued, so remember, so this concept which I had sort of brushed through, let me just sort of go slowly. That after this step 8 is finished, step 7, what you have to do is, you have to, of course, meaning collect the samples after waiting for time t, which is greater than typical equilibration time. That means whenever you have to, that means just like in tacit problem, you can again estimate. For instance, in this particular case, I can define as 1 Monte Carlo time step is proportional to n square flipping events. That means, remember, every time you're drawing the doing the trial move, what you're doing is you're choosing a site at random. And now, because your lattice size is n cross n, that means if I had called the random number or done the trial move n square number of times, on an average, I would be updating one lattice site. So this gives a measure of this many number of trial moves is equivalent to, in our language, 1 Monte Carlo time step. And like I said, the interpretation is the number of in this time all spins of the lattice of the system is updated on an average at least once. Okay. So now, just like in tacit, you can say that how the system would reach equilibrium is when you have many number of such events. Recall that in the tacit problem, we typically waited for 1,000 such Monte Carlo steps before we said that the system has in that case, of course, it was not an equilibrium steady state, it was a non-equilibrium steady state, but nonetheless, you had to wait 1000 Monte Carlo such steps to safely reach a state which was steady. In similar spirit, here we can, I mean, if you don't know anything about the problem, but I will discuss how you can actually look at when the system reaches the equilibrium. So the same thing to do would be, that means this step 9, wait for around 1000 Monte Carlo steps. But okay, I mean, in this context in TASEP, it was like you had to wait for around 1000 Monte Carlo steps. But here for this thing, you typically the numbers are, you would see, I mean, it will depend also on the temperature. But typically, even 100 Monte Carlo steps would actually ensure that the system has reached the equilibrium. And so you wait for that. And after you have waited for this, so when your T is greater than T equilibrium, then you start collecting the first sample. So so if I pictorially sort of draw it, you started with one particular sample. This was your T equal to 0. You have waited for 100 Monte Carlo time step, and then you have got your first sample, S1. You take. What do I mean by first sample? Of course, that sample would be defined by its configuration of the spins. No? So the whatever, it would be SI. So that would be your first sample. And if you want to do a time average, what you need to do is that you keep on again. So now you don't have to wait because the system is already reached an equilibrium configuration. You need not wait for 100 Monte Carlo time steps. In fact, even 5 Monte Carlo time steps are typically good enough. And then this would be your sample 2. Then you again wait for 5 Monte Carlo time step. You'll get sample 3 and so on. So now if you want to go get a reasonably good statistical thing, you basically take at least 5,000 samples, or at least minimum would be, I would say, at least 1,000 samples. So let's say 1,000, but ideally speaking 5,000. So you keep on doing this with the spacing of 5 Monte Carlo time step. So, and just like before, if you want to, for instance, find out what is the average magnetization for the system, so in this procedure, what is basically the definition of magnetization? The magnetization, so if I have calculated, that means what, after I have spent this much time, it is already an equilibrium sample. So the magnetization that I would be calculating for this sample would be the equilibrium magnetization, and that all I have to do is basically I have to sum over all the different spin states, right? I mean, basically there are there are n square spins, and this would give me the total magnetization for the system. If I'm asking the question, what is the magnetization per spin? That quantity I denote by small m. In that case, you would have to divide by n square. This is for a sample. And similarly, now that you are collecting after every in your code, you keep on collecting these samples for 5,000 times. And then if you want to find out what is your average magnetization of the system, then you have to, of course, if you are doing this averaging over 5,000 times, then whatever are the total number of samples, this is just the number of samples. And whatever is the calculated value, so this I runs from 1 to 5,000 for each of those samples, you can find out magnetization. I have just showed it for magnetization, but you can imagine similarly for each of the samples, you could have calculated the total energy for the sample. In that case, it would have been each of the samples, if they have energy E, then you would have to do again from I equal to 5,000 and divide it by. Okay, so all the different thermodynamic quantities, that means in principle all the equilibrium properties, you can find it in this manner. So today now what I am going to discuss now is all this procedure that I laid out. So what is the justification for doing this? How am I ensuring that this dynamics actually really reproduces the equilibrium configuration that one would expect? So I would today now discuss what is the justification for doing this procedure. But before I go into that, at least the procedure, how you have to actually drive the algorithm, what are the different steps of the algorithm. I hope it is clear how to go about it. Okay, one more thing which I should mention, and otherwise forget. And I just showed you one rough way of estimating whether the system is has reached the equilibrium. I told you that okay, typically 100 Monte Carlo time step is good enough for the system to settle to equilibrium. But actually, a more rigorous way of doing it. This is sort of. I just from prior knowledge, I told you that okay, one can ask the question why 100 Monte Carlo time step, why not 50, etc. So, what is the way? So, the question if you are asking numerically, how does one ensure the system has reached equilibrium? This question can be answered. One of the very clear-cut way, unambiguous way, is to see, look, you started with some configuration, initial configuration, and that time you calculated whatever was the total energy for this particular sample. Now, when you start doing this dynamics, that means you keep on flipping the spins for these different sides. Obviously, the energy that you see that will keep on changing as you keep on flipping the spin. Now, by definition, when you have reached equilibrium, when equilibrium is reached, then the signature of equilibrium is that things do not change in time. Remember, this is a very generic thing. No, like even for the case of tacit problem, there you were looking at average occupancy and average current. Those were the physical quantities that did not change with time. Similarly, even for an equilibrium system, like for this Ising case, that means any of the thermodynamic quantities that you look at, that means if you look at average energy for the system, or if you look at the quantity of even average magnetization, that should not, the average should not change, right? So the best way of looking at it is, since you are in any case calculating, even for one sample, you have, let's say you started with this value of EI. And then as you approach in time, that means, let's say this unit, I define one Monte Carlo time step. So let's say this is my, whatever, this is one Monte Carlo time step or whatever. Let me set some units. This is 10 Monte Carlo time step, 20 Monte Carlo, etc. These are my time. Then even for that one sample, as you keep on flipping the spin, the energy will change, right? Whenever one spin is flipped, obviously that energy, they would keep on fluctuating. But importantly, what you would see is that there are these fluctuations, but it will approach at some point. You would see that, it stabilizes to a particular value. You will see that here it might happen that here I have shown typically a configuration where the energy has started from a high value, whatever your random initial configuration is. And then as you keep on doing this trial move for large number of times, it will keep on fluctuating at each time step, but typically it would settle down to some asymptotically to some value. So let's say this is. And after it has settled down, you would notice that actually this does not change with time. Meaning you would notice numerically what you would notice is there would be some, of course, fluctuations, but it would be fluctuating steadily. You can easily make out even visually if you look at the profile that beyond. So you have to sort of have a cutoff that at what point you see that the system has very nicely settled into this, fluctuating about an average value. And then so for instance, in here, let's say this is let's say some 50 Monte Carlo time step. Beyond this, you see hardly, it is almost like a flat straight line which is parallel to this time axis. Then that means this was your initial, from your whatever random configuration you started off with. Here the interpretation of this diagram would be that means you have to wait for 50 Monte Carlo time step. That means at least 50 Monte Carlo time step you should wait before you collect your first sample, because that is when the system has settled to the equilibrium. Just as an additional point, it's not that it always has to come from higher value to lower value. Your initial random configuration might have been having an energy, average energy, which is lower than the equilibrium average energy. In that case, it might have started from this particular value, and maybe, in this case, it settles. That can also happen. So, apart from I told estimate by 50, you can actually, since you can just plot this energy as a function of time in terms of this Monte Carlo time unit, and from there you can explicitly find out from that plot that what is the correct, how much time should I initially wait before I start collecting the sample. This will unambiguously tell you that, so the criterion is basically whenever you see that your energy settles to a constant flat value and fluctuates about a common average, that is the minimum number of steps that you need to wait for before you start taking the sample. So this was as far as how operationally you would have gone about doing or equilibrating the Ising system. But now I will come to the justification. For this important sampling. Or by the way, so this specific trial move where whenever EF is greater than the final state is less than EI and you accept the move, otherwise you do this. This particular choice of this thing is also called metropolis algorithm. This restriction of how you do the dynamics using this trial move in this specific fashion where you scale these rates as, so that means whenever EF is less than EI, the probability of accepting the move is 1. That's what it means. And the probability of accepting the move when EF is greater than EI is simply e to the power of minus beta delta E. This particular choice of probability of implementing the move is what constitutes what goes by the name of this metropolis algorithm. And I must just mention as an additional point, this is not the only way in which you can generate the correct equilibrium distribution, but this is certainly one of the ways in which you can do it, but it's not unique. Now I come to the justification for importance sample. Crucial point is at equilibrium, and this is something very fundamental, not just for Ising model, but for any equilibrium system. At equilibrium, for any equilibrium system, including Ising, of course, the system satisfies detailed balance condition. And I'm emphasizing what exactly you keep on hearing. We kept on saying this detailed balance condition in context of STEM. Right? And so here we have to really carefully understand what does this detailed balance condition mean. So what basically detailed balance condition says is the following. In this context, at equilibrium, so what it is saying is that the initial configuration that you had started off with right at the beginning of the simulation, remember that is not an equilibrium sample. Equilibrium sample is when you have done the dynamics, the claim is that it has reached equilibrium, and if it has reached equilibrium, at equilibrium, if you look, the current, the flux from any configuration, that means you look at any particular spin configuration. That means, let us say I want to look at a particular, just for demonstrating it. Let's say this is a particular spin configuration I am looking at. Okay, this is corresponding. So this particular configuration corresponds to SI. At equilibrium, from this configuration, the flux or the change to some other configuration. Let's say I want to look at a configuration where one of the spin is flipped from this configuration. So that would be some other configuration. So let's say I have flipped this particular spin. Then my this is the this I denote it. So if I denote it by SI, let's say this other configuration is SF. So then the claim is that the flux, that means the rate at which this configuration changes to this, the total number of configurations changing from total, so not the total number of events that you would see of transformation from this particular configuration to this. So let's call it N forward. This would be the same as total number of events from this particular configuration to this. Okay, so this is the condition of detail balance. That means the total number of events from this in fact, I have just demonstrated it for two different configurations, but this would in general be true for all different configurations. That means for any particular ith state, if I look at how many events of transformation in given time, that means on an average, how many such events happen from where one particular set of this thing transforms. So that means there's like a flux from this state to the other state. This would exactly be the same from that transformed state back to the original state. So this is the meaning of detailed balance. So this is what I wanted to emphasize. Now, if I want to actually look at what happens, so if I want to find out, let's say, yeah. So in other words, if I denote from any configuration SI, the initial state, to the final state, this is same as the current from the final state to the initial state. Okay. So, whatever that means, the samples that I have been doing, it is not like I'm emphasizing, it is not that, when your system has reached equilibrium, things have started moving. The spins are still flipping. It is only in the average sense. So when I showed you that curve of the energy, it is only the average energy which has settled to a value. Similarly, the average magnetization would have settled to a particular value, and in principle, all equilibrium thermodynamic properties would have settled to that equilibrium value. But nonetheless, that rate of, that means the average flux from any one state to the other would be the same as the reverse. What it would mean is, so how do I estimate? So if I want to write down what is this current of SI, any configuration to the other configuration, clearly this quantity would be proportional to beta E SI. I'll write all of them. Let me then I'll explain the terms. Then let me use the notation. This term, first of all, how many events of transformation from a particular configuration SI to SF at equilibrium, all this thing is at equilibrium. First term is, that at equilibrium, any of the energy state are proportional to e to the power of minus beta. Right? So it is weighted by the Boltzmann factor. So this term, so let me call it A. This is just probability of occurrence of a particular state. Yes. This is the first. Then if you look at the second term, when you are actually doing the dynamics, this is the probability of occurrence of a particular state. PS is basically the probability when you are choosing. See, remember how we were doing the trial move was that we were choosing any of the sites at random for it to transform to a particular SF site, right? I mean, the particular specific SF site that I was looking was transforming to that where I was splitting only one state, and so that was the site I was looking at. So this is the probability of choosing a particular transformation. Right? And finally, the total flux would be proportional to, of course, the probability with which that particular state happens, the probability with which SI would transform to some, the probability with which a particular transition, I mean, you can think of that from SI, you could have, it could have gone to different states, right? You are choosing, I mean, each will have certain probability that, you know, you are looking at transformation from a particular, say, SI to SF, SF1. There could have been some other state, which would be SF2. So the fact that what are the relative probabilities of choosing that transformation from SI to SF, so it would be proportional to that. And the third thing is PT, which I denote by PT. So PT is just the actual probability of acceptance of the move. So if you, in this language of trial moves, so I hope you are convinced that this would be the the total current, how many events of transformation would happen, would clearly be proportional to the probability of, you know, first of all, that configuration occurring in the first place, and then subject to that, subjecting to the conditional probability that you know, you're selecting a chance of you know, a particular transition. And the third part is just saying that what is actually the probability of transition. So if you want to relate it with how we had prescribed the rules for the transformation, recall what was the rule that means from EI to EF, if your final energy state was lesser than your initial energy state, then the probability, that probability was 1 in that in our importance what do you say, metropolis algorithms. So, similarly, if the final energy state was greater, then that probability corresponded to e to the power of minus beta e. Point I'm trying to make is that that term is equivalent to this PT, the probability of a trial move actually being accepted or a particular event actually taking place. So this is this. Now, what we said was that if the system has reached equilibrium, then condition of detailed balance implies that this thing is exactly the same of transformation from SF to SF. Right? At equilibrium, this has to be satisfied. What is the meaning of this? That means if I had written this proportionality, all it would mean is this condition of, I mean, basically this condition. This would imply immediately, that means I have to equate this with E SF. Now the probability of selecting a particular transition from SF state to SI, and finally the probability of the success of a trial move from so probability of success of trial move in similar spirit would be PT SF to SI. And these two quantities have to be equal. Okay. Now, this guy, that means the probability that I will select a transition from SI to SF, the manner in which we are selecting the trial move, remember every time I'm selecting a site at random. So the P of S, probability that I select a transition from SF to SI, would exactly be the same of selecting a particular site SI to SF. So this thing would be exactly be the similar. What you are left with, so that means if I look at this ratio, PT SI e to the power of minus. So instead of using on this conversion notation, just let me write SF. This is equal to PT SI. Yeah, SF. Or in other words, if I look at this, I bring them all in one side. The probability of transition of an actual trial move being successful from the initial state SI to SF is probability. If I look at this ratio, so let's say I SF to SI. This is simply equal to minus right. So if the system satisfies detailed balance, a necessary corollary is that when the dynamics is happening, that means any particular state SI is going to some other state SF. If I take the ratio of the probability of the trial move from SI to SF and divide it by the probability of SF to SI, that should be equal to this e to the power of minus beta ESF minus ESI, or in other words, basically this is right. So this is just follows from the condition of detailed balance. Now, if you think of it, what we are doing in this specific metropolis algorithm is that's what I'm doing. What we are in fact choosing in metropolis algorithm of importance sampling. Your PT from SI to SF, this is exactly equal to 1 because you are accepting all those trial moves for ESF being less than. So as long as your final, the final configuration's energy is less than ESI, you are accepting this move. And similarly, that means if you had looked at the reverse transformation, that means from SF to SI, that the specific value that you were choosing was, so you were allowing that move to happen with a probability of e to the power of minus beta delta E whenever your delta E, that is EF, ESF was greater than. And so the ratio, so if you take the ratio of the forward move when you're implementing this condition, it is exactly what you would expect from the detailed balance condition, that you're allowing for this move. And in fact, so the dynamics of how you are doing this, implementing these moves for this Monte Carlo moves for in this important sampling exactly satisfies the detailed balance condition. So in essence, what you are doing when you are doing the dynamics is that if you had thought the system has reached equilibrium, the system's equilibrium dynamics happens in a particular manner. And what is that manner? That it happens in a manner where the probability or the transformation rates from the trial move from one particular state to another just happens to be is proportional to exponential of the energy difference between the states. And in essence, when you are doing importance sampling and doing this Metropolis algorithm, you are performing the dynamics exactly how it should have happened for the dynamics of an equilibrium system. And so the system basically, that means it respects this condition of equilibrium dynamics, and finally that actually allows the system to actually reach and settle to this particular equilibrium state. So are there any questions here? I mean, I provided a justification of how whatever we were prescribing is consistent with the condition of detailed balance, and in particular it is consistent with how the dynamics of the spin flipping happens at equilibrium. So this important sampling through this Metropolis algorithm respects this condition of detailed balance and does the job. So this was more or less what I wanted to discuss, but what you have to actually do is the following. I mean, I just described how you would actually do the samples, but finally, what is it that you are interested in looking at? And remember, our original goal was in particular to look at the the nature of the phase transition, how magnetization as a function of temperature behaves. So you want to use this simulation to reproduce the equilibrium characteristics of magnetization as a function of temperature. Okay, so how does that curve look like? So that means if you had found out the magnetization, average magnetization, and plotted it as a function of temperature, then so instead of temperature, what I would do is that I would plot it in the units of kBTJ. Then there would be a particular value of this kBTJ which corresponds to this kBTCJ. In fact, for Ising model, this number turns out, this ratio, remember, this is a dimensionless quantity. This is around, I mean, approximately this happens to be at the value of, I think, 2.27, around this, or 2.29. What you would observe is, if you had looked at this curve, the prediction for Ising model is that at n going to, that means if you had infinite system size, then the predicted behavior is that the average magnetization keeps on being 0. And then if you look at the magnetization, it would do either this or this is as far as the exact result that I discussed, that the exact result was by Onsarjan. So if you had done the problem exactly, that means at infinite system size, this is the behavior you would observe. That means if you had looked at this different temperatures or equivalently looked at, if you that means if you're looking at a value of kBT by J which was greater than this number of 2.27, you would find out, I mean, at equilibrium, if you calculate the average magnetization of the sample, that would be 0. Of course, there would be some fluctuations about 0. So this would be the trend. Whereas If you are below TC, then you will see it rising. And here, I mean, when I say +1, I am saying average energy per spin. That means I divide it by m by the average total magnetization by n square. And if you are going right up to temperature T equal to 0 or correspondingly kBT by J being equal to 0, then it would either be +1 or -1. Your purpose of doing this is to actually reproduce this curve. That means you would have to do, so if you want to get at least some of the points, what you should be doing it is, that means whatever prescription we described using this importance sample, you should take different ratios of kBT by J. Some points, that means if you want to, let's say you want to do, you take a point kBT by J, let's say this is 0.1, then do it for 0.5, then do it for whatever, 1, 1.5. Then 2.27. If you keep on doing that, in principle, you should get these points, right? So your job in simulation is basically to reproduce this graph. Fine, can note it down. And the only thing which would be different here is that, unlike this is the prediction for n going to infinity limit. But remember, typically the samples that you would be doing, the sample size that you would do is like you would do probably start with 10 cross 10, 20 cross 20. And you would go up to maybe maximum 100 cross 100. I mean, because beyond that, it would take much more simulation time in your typical PC. But let's say even with, so when you do for this finite size system, then this transition, which is very sharp here, in fact, I should emphasize it's sort of more sharp. You would see that at any, suppose if I had looked at, let's say I look at n equal to 10, let's say I look at n equal to 5, n equal to 10, then n equal to 50. Question is, does it replicate this curve or does it look different? And the answer is that you would start seeing variation. So if your system size is very small, n equal to 5, then you would see that it will actually not be so sharp. When you actually do the simulation, that when you calculate the point, you will see that the fall is much more gradual for n equal to 5. This is what you will actually see when you do the Monte Carlo simulation. Let's say now I compare this n equal to 5 with n equal to 10. There, if you do, you would find that even here it is not so great, but it is at least, it falls off much sharper as compared to the n equal to 5 sample, and it will do something like this. And to illustrate, if you actually typically go to n equal to 50 or more appropriately, if you actually go to n equal to 100, then you would see that it is almost, it will not exactly, here the actual curve is, it sort of flatly goes to 0 and then it is 0. For n equal to 100, it was really close, go very close. This transition, you will clearly notice that if you go to higher and higher system size, this transition will become sharper and sharper, and this transition temperature, whichever is the predicted transition temperature of around 2.27, it will start approaching that, and that is what you will observe in your simulation. So in your program, this is what you would have to do, that you have to reproduce this graph of m versus kBT by J. In fact, I'll also send a sample reference of what people have obtained for different system sizes, so that you have a way of knowing and comparing whether your simulation results are correct or not. Okay, so you can, I mean, for today I have finished. So if you have any questions regarding this, you can go ahead and ask. So tomorrow again, I'm going to take one extra lecture, and maybe on Friday, but definitely tomorrow. So tomorrow, briefly, I'll just very quickly again summarize this Ising model, what you have to do, how you write the code, maybe some outlines of the code again I will show explicitly. And then I would move on to molecular dynamics. So since in this, because of this particular corona thing, we didn't have enough time. So I would not go into the details of molecular dynamics simulations. How I plan to do it is that I will actually show it for very simple cases for a 1D system. And in fact, yeah, so the last program, so there would be, I will show you how to actually code for even molecular dynamics simulations, but at least as far as the final exams are concerned, that question will not be compulsory. So even if you do not manage to finish the numerical code, but not the theory. Theory would be part of the syllabus. But if you do not manage to finish the code for the molecular dynamics simulations, that would not be part of the compulsory at least question for the final. That might come as an option. But until here, that means I expect all the programs. I formally, like I said, I hope you have started beginning with the tacit problem. The tacit problem and the Ising problem, whatever like I described here, that is very much part. So until basically the Ising model, whatever I discussed, that's at least part of your final syllabus for even the programming part and would be part of the assignment. So the two major programs that you need to do apart from whatever we have discussed is of course the tacit which you have to do and this Ising model that you have to do for different temperatures. Like I said, you have to reproduce this curve of m by n square as a function of temperature and go through in between all these procedures for that. And so you better start doing the code because it will take a while. But this is part of the syllabus. If you are not doing, obviously there will be consequences in terms of what you will score and things like that. So I'll stop here if you have any questions, and tomorrow again we would meet at the same time. So let's say instead of 1:30 because the previous class goes on, we will start at 1:35. So 1:35 we will start tomorrow.
Sir?
Yes.
Sir, you told that there will be a doubt session.
No, so what I will do is, so this week, so that's how I'm planning it. So whatever I have to do on the blackboard, that I'm planning to finish either tomorrow or if we require one more class on Friday. So the aim is maybe I'll try to finish it tomorrow. Whatever are the, so as you start doing the program, see, because finally this is a course, this is a hands-on course. I mean, what I tell in the lecture is very small part. You have to actually do the coding. I told you the outlines. Now you can do the code. So the next week we can have doubt sessions where if you are having the code or any problem of the code, the usual timing. So maybe next week, like even from 1:30 to 2:30, I'll be there. I'll be there online. So if you have any specific doubt, you can ask me. But basically, whatever is the theory part or the theory part that I'm describing, that sort of finishes. I plan to finish this week, after tomorrow or day after tomorrow. And so you will have time the entire of next week or whenever. So the usual class timings, instead of usual class timing, we'll probably have from this 1:30 to 2:30. You can have like thrice a week or whatever. So that would be there for the. So don't worry about it. So that would be there even next week.
Okay, sir. Thank you.
But like I'm saying, you have to start doing it, and what your internal assessment marks will depend on what assignments you have submitted and how successful you have been. I can only outline the steps that are to be done. And like I mentioned that, please do not ask me doubt about, my program is not compiling. I mean, that is expected for you to sort it out. We can discuss. So I'm saying, if you find that conceptually in your program, I mean, don't come to me saying that my program is not compiling. Now, that you're supposed to know how to write a correct Fortran code in your last semester. But you can come and definitely you're welcome to ask any point of time. If you are doing the simulations and you're not able to see if there is some, you're not reproducing those results, or you see your dynamics is not happening. So of course, I mean, at any point of time, we can next week we'll discuss all these questions. That any part of the code, if you find that it is not reproducing what it is meant to be, we can look at those issues and discuss that where are the errors you are making. So any doubt for the last two classes? And in between sometime, I would try to forward you, if I find a PDF file of this Frenkel and Smith. Have any of you found it already on the internet? Yes. So very nice. So if you have found it, please also share with your friends. I'll also try to get.
Sir, but it is 100 MB above.
Okay. Yeah, so I don't know. I mean, some way of you can mail it to your friends if you can. Let me also see if I get.
It is easily available.
Yeah, it is easily available. No, yes. So I guess so. So in principle, people can access that I mean, you have to basically, it is there, I forgot, the first chapter or second chapter. I mean, all this thing that I described for the last 3-4 classes regarding importance sampling, how you go about it. The conceptual things are discussed in fairly great detail. In fact, it's a great book. Great book in the sense this Dan Frankel is really the big boss in this field, numerical simulations. So you should really seriously have a look if you want to have a more detailed understanding. And in fact, in this book, you'll find there's much more than what our course allows us to do. So if you can, please share it with others. I'll also try to find, and if it's possible, I'll try to upload and sort of complement it with some other handwritten notes. So any other doubt? Otherwise, I'll stop the lecture for today. Okay, so then I'll stop the recording.